Okay, right now we are going to do some examples of identities from the section on Pythagorean sum and difference identities. So let's start by some simple ones. Very first example is very straightforward, just asking you to practice sum multiplication. In the next section, there is going to be more requirement on exactly same question. So let's see what is meant here. Here, this problem is just asking you to multiply and simplify. So again, we have that dreaded word simplify, which is what you are going to learn by doing all the 80 problems here, what is meant by that question. So we say, in this case, sine of x times sine of x, we said, we abbreviated in this style, sine square of x. Cosine times cosine minus cosine square of x. Now, if you remember an identity from college algebra, you know this is the end of it. Otherwise, you might go ahead and say, well, how about sine times cosine, and then minus cosine times sine? What happens to that pair? They cancel out. So this is an example of this identity, which if you saw it this way, we would have done it right off the bat without wondering about what happened to the other things. Difference times the sum is difference of squares, and that's an example of it in trigonometry. All the questions from 1 through 8 is just asking you to practice that type of multiplication. For example, something a little bit more substantial. Sine of x plus cosecant of x times sine square of x plus cosecant square of x minus 1. There is a shortcut formula. Let's see, those of you from college algebra, anybody remembers? So let's see. There is something like that for higher powers as well. It goes like, say, a plus b times a squared minus ab plus b squared. That is identity for cubes, factorization of sum of cubes. Typically doesn't get enough emphasis, so you might not remember this. So let's just go ahead, actually multiply it out, see what we get. So I take one term here, multiply by everybody there. Tell me what I'm going to get. A times a cubed minus what? Plus a b squared. Is that right? Now, take the second term, multiply by everybody waiting on the second parentheses. What do we have? So, what happens? This is same as that, and this is same as that. So I get a cubed plus b cubed. So we have such an identity. Now if we had seen it in advance, we could have said that I have sine x, cosecant of x, but does this thing really match that? So let's rewrite. Sine of x plus cosecant of x times square of this. I do see square. I see the square of the other one. The other term is supposed to be the product of first and second. What is sine times cosecant? What is sine of an angle times cosecant of the same angle? Yes, very good. So when you multiply them, what do you get? 2 times 1/2 is going to give you 1. So this term that is in the middle, minus sine x cosecant of x, which is supposed to be there for AB, this has been condensed to already to minus 1. All of this is minus 1. So it's not a big surprise that at the end I'm going to get sine cube of x plus cosecant cube of x. So that was a little bit more substantial than. Now, how do we know this is the end of it? Can I do other stuff to it? Could try, but that's good progress. Next bunch of problems ask you to factor, and I guess the question that you asked me is, it's not exactly one of these, but let me get some of these problems done, then I come to your question. We have factorization problem. Let's start with something straightforward. What can we see as a common factor here? So this problem 9. What can I factor? Cosine of x. What this is trying to teach you is that cosine of x, all of it is one item. Cosine of x, this has to be written like this. Any other writing indicates that the concept of function hasn't been understood. So this is really the only way to write. Is there anything else that can be done? No. It's like that's how far I can go with this thing. Some other examples take you to stuff from, let me do something easier first. 12. 4 sine square of y plus 8 sine of y plus 4. You can factor over 4 sine square of y plus 2 sine of y plus 1. What else can I do? Well, 4 is just 4. I look at this, it has to remind me of a certain identity. Well, what is the factorization of it anyway? Let me ask you. A plus 1 squared, what is that? A squared plus 2a plus 1. Do you see this is same as that? Your a is sine of y, twice it is here and a 1. So this is really just sine of y plus 1 squared. So it's asking you to factor, and that is our factorization. So many of these things remind you of the factorization back in college algebra. Problem 15 is going to be a little bit more substantial, but let's go ahead and do one of each type and not get stuck on one. Yeah, question was asked by Peggy on this from the software. Cosine of x over sine square of x times sine of x cosine x minus 2 sine of x. This is the exercise from software. I don't know what number it is. Problem 20. Okay, 20 from the software. Cosine square of x minus 4. Okay, what can we factor around here? I look at this thing, I say, from numerator of this thing, what can I extract? Yeah, so I extract the sine of x, and then what is left inside? Cosine of x minus 2. Is that right? So I can write, since they are being multiplied, I can write them next to each other. 9 cosine I already had. This sine, I took it out. This sine, I took it out and wrote up front. Everything else is as before. Then we are dividing denominator. I don't have much to do with it yet. Now I think about simplifications I can do. What can I cancel? This sine squared means a sine times another sine. One of them can be taken off with that. So maybe I write out everything. Sine of x, cosine of x minus 2. Sine squared means sine x times another sine x. While we are writing it out, let me see if you can suggest a way of breaking this one apart. Cosine of x minus 2 times cosine of x plus 2. Okay, now all we can do is to take out some of these things, and now we are back to 9 cosine x over sine x times cosine x plus 2. You could always go ahead and say this is cotangent, but that is as good as we could make it. Now, with respect to these type of questions, the book, you might come to a certain stage, the book might tell you, or the software might tell you your answer is right, but it's not the final answer. It does ask for that. So you say cosine over, that's where things become kind of arbitrary, where to stop. It becomes 9. Cosine over sine is cotangent of x. So maybe that's where you were missing. Another question. I suppose we can try the second one, which is pretty similar to this one. Is that right? So let me leave that to you to try. So let's do another one of these questions. Let's, if you have any suggestions, just holler. So problem 27. 1 over sine square of s. Instead of s, let me write something else because my signs already look like s. So sine square of x minus cosine square of x minus 2 over cosine x minus sine x. What we are doing here, practicing common denominators. We want to work on the lowest common denominator, because just multiplying them out as it is going to make a horrendously complicated expression. Several things we can do. Since sine is first year, I might try to make this sign come first as well. Anybody can suggest how to accomplish that? We can proceed as it is, but our life is going to be a little bit easier. That minus can be in front, can multiply numerator, or can multiply the denominator. So I choose to multiply with the denominator just so that the two expressions start with the same piece. They are both with the sign. It wasn't essential, but it makes things a little bit nicer. Now, this denominator, what identity do we remember from college algebra to break this apart? Difference of squares can be written as difference times, what's the second piece? Plus cosine. Now we are taking common denominator. That common denominator, essentially delivering everybody into the same denominator. This factor is already here. Now it depends how much of a practice you have on this thing from high school. just to see what happens. This denominator is not same as that. To make them the same, I can multiply by the ones that are missing. Who is missing? Sine x plus cosine x is missing, but I'm not just allowed to multiply just to make it look the same as that. I have to multiply also the numerator so that my fraction hasn't changed. That is what you do when you take common denominators. So, okay, this is common denominator, it matches this. The contribution from the first one is just 1.
I have a question.
Yes.
How did they go from minus to plus? How do you
From here to here?
Yes.
Yeah. As mentioned, if you have a fraction like minus 2/3, you can write it as minus 2 over 3, or you can write it as 2 over minus 3. So this fraction that I had was minus 2 over cosine x minus sine x. If I want to, I can let this minus to float in the denominator. That is 2 over minus cosine x minus sine x, which is minus minus makes it plus, minus cosine. So this minus can be used to flip the flavor of each of these two expressions. Cosine becomes minus cosine, minus sine became plus sine. Okay? Okay, what is left here is 2 now again, it all depends what you consider to be simplest. This is good enough. On an exam, this is as good as it gets. In the software, sometimes you have to hammer it around until you agree with the software as to what is the form that is requested. So that is a tricky issue. So either this or that could be sold as final answer. Then a little bit of practice on multiplications and radicals. Let me remind you of something from college algebra. What is radical A times radical B? Yeah, this is true so long as definitely true for A and B being positive numbers. Here it says assume all radicands are non-negative, meaning we are not dealing with the issue of complex numbers and things like that. We are just keeping it simple. Another issue is what's radical x squared. We said last time that this is absolute value of x. You generally like to say square root of x squared is just x. That is true if your x is non-negative, which is in all cases in the problems you are being asked here. Let's take one of these things. This is what is radical sine square of x cosine x times radical cosine x. Several ways to proceed here. One is multiply the radicands. Next, square root of an item squared is just that item if that item is non-negative. And that is so for all of these problems. It says we are assuming stuff in the radical are non-negative. All the bases. It's not so clear. 33. Let's see what we can do with 33. So this is assuming sine of x is positive, cosine of x is positive. The book. Oh, the book is just saying let's make things simple. It says all radicands. That's not all that clear what they mean by all radicands, but all radicands. Let's make it like this. Anything in sight is positive. All radicands are non-negative. So I suppose the book doesn't want to deal with absolute value issues. It says, okay, assume anything that you are dealing with is positive. Okay. So 33. Otherwise, we had to make absolute values, exemptions, and such. 33 says radical cosine alpha sine square of alpha minus radical cosine cube of alpha. Okay, a standard trick that is applied is if you have radical a times something squared, you can take out the square portion out and the other portion can stay in. Where does this come from? Is really reverse of this rule. If you have ac squared, you can write it as radical a times radical c squared, and then c comes out. Again, just to keep things simple, all terms are considered non-negative here to keep problem from having absolute values in it. So here, with respect to that, if I want to simplify this, how can I write it? Let me write the missing step also, and then I continue. Cosine alpha sine square of alpha. This is, I'm going to break this into two portions. Cosine alpha, cosine square of alpha. So cosine cube was written like this, so that we are forcing this look like that, and also extract the perfect square component. So sine square of alpha comes out, just like here the c came out. When this comes out, what do I get? Here is also cosine alpha square root. We are expected to factor some exercises from the kind of identities we were just doing. Let's see, 57 says sine of 37, these are all degrees, I'm not writing degrees in book, plus cosine of 37 sine of 22. This is forcing you to remember your sum and difference formulas in reverse. First of all, which identity is it? Is it for a sine or a cosine? Sine. When you have mix in each term, indication of a sine. Let me remind you what the identity was. What was sine of? A plus B was sine of A cosine B plus cosine A sine B. We didn't prove this, but we are running out of time. We proved the cosine one. Once you have that, everything follows quickly in quick succession. You can read in the text how the proof happens. But here it's just asking you to remember this in reverse. Remembering identities in reverse is a bit tricky for students. You typically go this way. You see that, you remember this. But you want to also know it in reverse. It's called the pattern recognition. So what do we get here? It's a sine of 37 plus 22. It's sine of 59, whatever that happens to be. So that's the exact value. Remember, we don't want calculator produced example. You can type all of these things on the calculator and give me something reasonable, but that's not necessarily the reasonable answer. So let's do another one, 61. tan 20 minus tan 32 over 1, no, plus, minus tan 20 tan 32. Again, we didn't practice this formula that much, but that was the formula for tangent of A plus B. Make sure you also practice tangent of A minus B. So this is an application of this identity. What's that going to be? Tangent of sum of the two angles you are working with. 20 plus 32, 52. A lot easier than the okay. So you bring up the remaining questions tomorrow, and tomorrow we try to do section 2 too.